please put it on upside down. I know that the mass is going to be somewhere around 500, just because I've done this before. So somewhere between 510 and 520. Probably good enough. So 518.63. So 518.63 minus my offset, minus 0.38. Doing the fancy math here. 5.2, so 518.25 grams. So my mass of cart, 0.51825 kilograms. We have our formula here. We know this is Winston-Salem, so G, what is G?
9.798 meters per second squared.
There we go. So if we plug our values in, what do we get? What is our predicted acceleration? Juice that thing, yes. I've got the plug in case we need it.
I've got 2.1728 meters per second squared.
There you go. Ethan, you get the same thing?
I got the same thing without the one.
Oh, 2.728?
Yeah, sorry, I didn't mean to say one.
Oh, and
Sorry.
I might have misheard. So 2.728 meters per second squared. All right. What are the chances we're actually going to get anywhere close to that? So what we're going to do is use a motion sensor. Now, the motion sensor is measuring position. That's all that it measures. And hopefully you can actually see it just says position there. It does not measure velocity. It does not measure acceleration. It calculates those. And it calculates it based upon, there's certain defaults. It goes in, you can do it simply or complexly. The more complex you do it, in some sense it's more accurate, but in some, by taking a certain number of data points, not only does it look at the rise of a run for, say, for velocity, not only does it do rise of a run, but if I could do 3 data points and it'll look at, well, this is the average here, so the average of those two would be closer, or you can add more points to it and it takes more and more of a curvature into account. Acceleration will be based upon those calculations. The trouble is that the more complex you make it, or the more number of points you take it, it'll be more accurate unless you start taking into account things that are outside where it was actually moving. Let's see. Now it's restarting. So let's add this in so the screen doesn't go dark on me. Say it again?
Start fire reliably for the day.
Yes. That's on. I think it's working. So what we're going to do is we're going to use this to come up with a graph for position. We'll find the equation of that, and then from that equation, we will be able to figure out what the acceleration is. Now, because the motion sensor is pointing this way, I don't want it to have issues with the plunger here. I put the plunger on that side because this has the hole to which to tie the string. So we just want to retract the plunger so that it doesn't get confused by hitting the plunger one moment and hitting the side of the plunger the next moment.
What's the plunger supposed to do?
There are experiments that you can do. If I could have the cart with the plunger here and the cart next to it, hit that, and they'll be shot apart, or usually momentum experiments. Now there is a variation of this lab where you figure out how far it goes, and then you'll do basically chapter 2 calculations, but that gets really picky. There's also a magnet here, so that when I move this, if I just jerk this away, probably would move the cart with it, and I want to avoid that. Is that string level?
No.
Which way does it need to go?
The left needs to go up more.
One. A hair more. Maybe a nudge more.
Feel like it's still not that
A
level.
little more.
Maybe.
If you could blow on it upwards, it'd be level.
All right. Just go back down.
Yeah,
Okay.
I am.
At some point, there's a certain amount of close enough, but.
That's a close enough, sure.
All right. So we're going to start this off. Now, let me do this awkwardly. All right. So we have the two graphs here. I'm assuming that you can see the graphs. I got it angled correctly. What I care about is the position graph, so let's take a look at just that one. So graph, show graph 1. All right. Now, this is before I released it. This is after it hit. So what I really want is just this section here where it's part of a parabolic curve. So I'm just going to highlight that graph, zoom in. All right, so I've got it a little bit more precise there. And whoa, what's that? So I'm going to take just a chunk of it where I know that it was good data, and to analyze curve fit position. It takes me to that screen. I don't know if you can see the little black brackets on the line there, on the red line. You can see it, you can see it. There are little brackets there. That's what's going to be modeled. It's going to look at those data points between those two brackets when it actually comes to coming up with a curve. I don't want a linear because I'm not expecting a linear or quadratic. And now there's a black line that's overdrawn, the black line which basically should match the points pretty well. I've got several different bits of information here. The RMSE is the root mean square error. You want that as close to 0 as possible. Anything off of 0 tells you how that things might just be a little bit off. However, we do end up with, not too bad. Let's get rid of some of this. That the position of the translating part of it, with it as a function of time, is equal to 1.3344. Negative 59,377. Something. The OCD is 8248. All right. Now let's take a look at units here. I know that this is in meters, which means that each of these terms also needs to be in meters. Well, clearly that would be meters there. What would be the units of this coefficient then?
Meters per second.
Yeah, because I'm multiplying by time, which would be in seconds. So this would be meters per second, and this would be.
Meters per second squared.
Now you had a master set problem like this where you had the equation and I asked you bits of information. What we care about is the acceleration. What is the acceleration?
.668.
Because this is 1/2 AT squared plus VIT plus basically the initial position. That coefficient is half the acceleration. So we got an acceleration of 2.67 meters per second squared. We predicted 2.73. Not too far off. The fact that this acceleration is a little bit less than what we predicted makes some sense because you could easily explain there's some friction in there somewhere, which would make it not quite as fast. All right, questions to there?
Taking the derivative also works, right?
Yeah.
So I did because in my head I just did the t. I did the 2 times the number, subtract 1 from that exponent.
Yeah.
And I just did
That, absolutely. I mean, the reason why this is true is basically if you do the 2 derivatives, you end up with acceleration equals acceleration. Or start with acceleration equals acceleration and do 2 antiderivatives. Other questions? This thing is still going. Okay, so let's do the box on ramp problem. Again, we're going to assume one of the reasons we want to eliminate friction is that it's a pain. But these carts here are pretty low friction, and you can sort of tell spinning the wheels will spin for a bit before stopping, similar to the pulley there. The carts that we had when I first got here were old and clunky, and friction was far more of an influence there. So this time, what we're going to do, instead of that version of Newton's second law lab, we're going to put it on an incline. And what I don't have is the angle indicator. See if there's one lying around. All right, I'm going to go grab an angle indicator. I'm just going to let that run. I'll be right back. All right, so we're going to put this at an incline, and I need something on which to prop it. Then it's not going to be stable like that. Hopefully that will be stable enough. So we're going to put the cart on it and have the cart come down the ramp. We know what the mass of the cart is, and it was written up there at one point. Hopefully somebody has it written down.
0.51825 kilograms.
0.51.
825.
So what is the weight of the cart? Let me get rid of this stuff. Yes, it is. All right, I assume you'd use 9.798?
Yeah.
Okay. All right, so we have the weight of the cart. The angle of this cart put it flat there. Or the angle of the ramp is, it's in 20 pretty darn exactly. Just slightly lower. We'll go to 20.1 degrees. So we have cart on, this is in essence box on ramp, frictionless ramp, this angle here, theta. I have weight acting down, I have normal force acting this way. What is the direction it will accelerate? Okay. So when I set up my coordinate axes, how should I set them up? That second finger gesture, I wasn't quite sure which way you pointed it.
The direction the normal force is perpendicular to the direction.
Okay. And I'll just call I hat, J hat. Decomposition. Are either of those vectors, I have two vectors there, either of those vectors not parallel or anti-parallel to my axes?
Is weight supposed to be going straight down?
It should be straight down. Is that ish? All right, so weight has to be broken up because it is not parallel or anti-parallel. Anti-parallel just meaning opposite. So we have to figure out how much of the weight is down the ramp, how much of the weight is into the ramp. How much of the weight is down the ramp, how much of the weight is into the ramp. So weight, since we are breaking that up, that is our hypotenuse. And some of it is this way, and some of it is that way. That should be a right angle. Now I have a triangle right here. I know one of those angles is going to be the same, it's going to be my 20.1 degrees. Whatever theta is. One of these angles here is theta. So let me just sort of extend that. Let's see, that out. I know this angle here is theta, and that's a right angle. This angle here must be the complement of theta, with 90 minus it, which I'm going to label as theta prime. I know weight is acting straight down, so that's a 90-degree angle there. So this angle here must be theta. So now, breaking my triangle up, my hypotenuse is W. My opposite side is the one dealing with sine, so this will be W sine of theta. And this one right here will be W cosine of theta, which is So what I'm claiming is that my force diagram looking like this can also be written as I have normal force acting this way, I have W sine theta acting down the ramp, W cosine theta into the ramp. Let's do our equations of motion. So what are my two equations of motion?
Normal force minus W cosine theta equal to mass times 0.
Okay. And the other one?
W sine theta equals mass force mass times acceleration.
Substitution phase, I just have my weight there, so I got mg sine theta is equal to ma. Solve for A.